So welcome to the third page, or third topic in special relativity. In this topic, we will start to actually look at the theory of special relativity. So in the previous video, we saw that under the Galilean transform, Newton's theories and Maxwell's theories couldn't both be correct. And so we figured that we had something wrong. We thought we'd have a look at the other theory, but that was disproved by the Michelson-Morley experiment. So we still have a big unanswered question about how we can somehow relate or join these two seemingly fundamental theories of physics. So this was a big puzzle for a while, until a man called Lorentz came up with the suggestion that, well, perhaps the transform is the incorrect part, so perhaps we need to use a different transform. And so he knew that the Galilean transform at low speeds was correct. And he said, well, okay, fine. So what if we have a slightly different transform at high speeds, at relativistic speeds, which is the Galilean transform just multiplied by some factor gamma. And we have it such that that factor gamma approaches 1 at low speeds. And so then both the Galilean transform and Newtonian physics are correct at low speeds, but we have the explanation that also includes what we see at high speeds. And this transform was then later called the Lorentz transform. And we'll look at that transform itself in more detail in a different video later on. So what Lorentz had done was said, well, look, we can make the maths work. But what he hadn't done was find the physical reason or the physical idea or theory that let both Maxwell and Newton be correct. And that was done by Einstein. So Einstein's genius was that he figured out how this could work. So he figured out the physical theory or the explanation as to how both Newton and Maxwell could be correct. And to figure that out, it required a completely new perspective on the way the universe was put together. So he rewrote physics again. It is not often mentioned in the textbooks, so I will just mention it in passing here. But Einstein had already been and continued to work closely with Lorentz, and Lorentz was one of the first and one of the most constant supporters of Einstein's theory. And the maths, the Lorentz transform, is such a big part of the theory that initially it was called the Einstein-Lorentz theory. So the basis of Einstein's theory was two rules or two postulates. And these are that the laws of physics are the same in all inertial reference frames. So this is an extension of Newton. So Newton said that his laws of motion were the same in all reference frames, all inertial reference frames, and Einstein extended it to say that that must hold for all laws of physics. And the second postulate, or the second rule, is that speed of light in a vacuum is constant. And this was the inclusion of what Maxwell had derived and what had been experimentally observed. So it said that the speed of light doesn't change with the speed of the observer. And this is in fact a property of all electromagnetic waves, or all waves. For example, we know the speed of sound in air, we know its value, 340 meters per second. And that value, it depends only on the properties of the air. So for example, how dense the air is. But it doesn't depend on the speed of the source. So the speed of sound in air is also independent of the speed of the observer. So these two postulates, they seem very logical and they seem simple enough, and that they are. But they lead us to some very surprising results. So over the rest of this topic, we are going to be learning a new way of looking at the universe, and it's a way that's completely outside our everyday experience. So quite a few things that we can conclude are going to seem to us to be impossibly strange. And the key thing to remember, or the key thing that I try and remember, is that these postulates, these rules, they're our two constants. So they're the basis from which we start our logic and our reasoning. So we're starting from these two principles, or these two rules, and we're building up our universe view from there. So on the rest of this page, so in the next video, we'll be looking into the first of these somewhat surprising results, which is to do with simultaneity. So it's to do with how we define and how we perceive that two events are simultaneous, so that those two events occurred at the same time. And the way that I would like to do that, so I think one of the more useful ways of looking at simultaneity is using space-time diagrams. So to start with, we'll look at the concept of space-time and the coordinate system that we use to describe it.